So we're presented here with some data relating to a random variable x and a random variable y, and we suspect there might be a relationship between y and x such that each observation of y is equal to some beta times by the observation of x plus some random error term. So this is how we suspect that the data has been generated, and we want to try and estimate this beta, the relationship between x and y. Now we're going to try and estimate this relationship by effectively drawing a line of best fit through our data, which might look like this, or it might look like this, or it might look like this, for instance. Now the only thing that's constant in all of these lines is that we've constrained our relationship such that the line passes through the origin. Now, how are we going to estimate the size of beta? Now remember, the beta is just the slope of the line. So each of these lines, we have three lines that we've got here, each of these three lines would have a different slope. So we'd have a different slope associated with each of these, so we'd have a different beta hat related with each of these. So what would be the optimal beta hat? Well, what we're going to do is we're going to use the OLS estimator. And the OLS estimator looks at the sum between I is equal to 1 and n, where n is the total number of observations, of the product of y and x divided through by the sum of the x squareds. So in order to calculate this, let's add another couple of columns to our table of data. So we're going to have the observations of y multiplied by x, because in order to construct our estimates, we're going to need y times by x for each observation. So when x is equal to 3, y is equal to 2, so y times by x, or x times by y, is going to be equal to 6. Similarly, when x is equal to 4, y is equal to 1, so xy is 4 times by 1, which is 4. When x is equal to 5, y is equal to 3, so x times by y is 15. And similarly, when x is equal to 7, y is equal to 4, so xy is equal to 28. And x squared, the denominator of our estimator looks at the sum of the x squareds, so we're going to just be looking at 3 squared plus 4 squared plus 5 squared plus 7 squared, or 9 plus 16 plus 25 plus 49. So if we now substitute these numbers in to our OLS estimator, so the numerator is just equal to the sum of the y-x's, so it's going to be 6 plus 4 plus 15 plus 28. And similarly, the denominator will be just equal to the sum of the x squared, which is 9 plus 16 plus 25 plus 49. Which is going to be equal to 53 over 99, which is equal to 0.53535353, and so on, or 0.53 recurring. So what does this mean? Well, this is our estimate of the marginal impact of a change in x on y. Our beta hat is the estimate of a marginal change in x on y. This estimated relationship suggests that when x increases by 1, y would be expected to increase by 0.53 recurring. So our estimated relationship, yi hat, is equal to beta hat xi. Our beta hat is the estimated marginal effect of a change in x on y. And the estimated effect here is that a 1 unit increase in x would be associated with a 0.53 recurring increase in y.